Okay, I think the recording has started. Please take it away.
Okay, awesome. Thank you, Joanna. Hi, everyone. Thanks for joining today. My name is Wing, and today Maulik, Ulf, and I will be talking about PSCI OS initiated mode in TFA. So we'll first give a brief intro to power state coordination, and then talk about why and when OS initiated mode might make sense, and the current vendor implementations and workarounds that exist. We'll go over the overview of the proposed changes for OSI mode and the testing that we've done. And finally, we'll go over the requirements as outlined by the PSCI spec and the implementation details in TFA. And then we'll have questions at the end. So a power domain topology is the logical hierarchy that arises from the dependencies between different power domains in a system. Local power states are the power states that a particular power domain supports, and composite power states describe the combined power states of a power domain and its parents. So what we mean by power state coordination is the coordination of children power domains so that we can put a parent power domain into an idle state. So let's take a look at this example power domain topology. This is from the spec. Here we have 3 power levels. We have the core level, cluster level, and system level. There are 4 power domains at the core level, and 2 at the cluster level, and 1 at the system level. And then we can see that each power domain has their own supported local power states. For an example of power state coordination, cores 2 and 3 would have to be powered down before we can power down cluster 1. So there are 2 modes of power state coordination. We have platform coordinated and OS initiated. Platform coordinated is the default per the spec, and right now it's the only supported mode in TFA. This is where the platform keeps track of the composite power state requests coming from each core for the core itself and their parents, and then the platform chooses the deepest composite state that's allowed by all the requests coming from all the cores in the system. OS initiated mode is optional. This is where the OS is responsible for coordinating the power states, and the OS may choose to request for a composite power state when the last core in a power domain goes idle. So let's go back to the previous slide just to see an example of each mode. So in platform coordinated, when say core 3 goes idle and requests for itself and cluster 1, its parent, to go to power down, the platform at this point can only power down and will only power down core 3 since core 2 is still running. But when core 2 also goes idle and requests for itself and cluster 1 to power down, this is when the platform will power down both core 2 and cluster 1 since both cluster 1's children are now powered down. Whereas in OS initiated mode, when core 3 goes idle, the OS will only request for core 3 to power down. And then when core 2 goes idle, if the OS sees that cluster state is appropriate, it will request for core 2 and cluster 1 to power down. So why OS initiated mode? There are 2 reasons why it might be a better option than platform coordinated. The first is scalability. In platform coordinated mode, each core selects their own idle states independently and doesn't account for cluster idle states that are shared between cores. In OS initiated mode, the OS has knowledge of the next wake-up event for each core and can decide when cluster idle state is appropriate. This is especially important for multi-cluster SMP systems and heterogeneous systems like Big Little, since different processor types can have different power efficiencies. And the other reason for OSI mode is simplicity. In platform coordinated mode, the OS doesn't have visibility in the last core of a power domain going idle. So if the OS wants to perform what's called last man activity, which is when the last core of say a cluster goes idle, such as powering off a shared rail, it will have to communicate with an extra API side channel, aside from TFA. This could result in a design smell where the platform is using platform coordinated mode, but actually wants to be using OSI mode. In OSI mode, this problem goes away. The OS can perform last man activity when the last core goes idle. So we eliminate the need for a side channel, and we're using the well-documented API between the OS and the platform. So these are the vendors that are currently using either custom implementations or workarounds for OS initiated mode. ST Microelectronics right now is using OSI mode. They implemented it in OptD for their ARM32 platforms, since that's what they're using as their secure monitor. But they're interested in using TFA for OSI mode in the future on their ARM64 platforms. Qualcomm's mobile platforms are using OSI mode implemented in their own custom secure monitor firmware. And Qualcomm's Chrome OS platforms and Google's mobile platforms are currently using platform coordinated mode in TFA, but with custom OS driver logic to perform last man activity. And both Qualcomm and Google would like to switch to OSI mode in TFA so that we can simplify that custom driver logic. So the stack of proposed changes can be found at this link under the PSCI OSI topic. Two things I want to highlight before we jump into the implementation details later is that support for OSI mode will be guarded by a build option. So it will be up to each platform to decide whether or not OSI mode makes sense for them. And another thing to note is we're enabling the support for OSI mode on the FVP platform and also the SC7280 platform. So for testing, we added a new CPU suspend in OSI mode test suite to TFA tests. This has been enabled and tested on the FVP platform and the Google platforms, and is excluded from all the other platforms in TFA test via the build option plat test skip list. And it essentially uses the same similar structure as the current platform coordinated CPU suspend test suite. It's just the main difference is that we are coordinating the states that we're sending to the TFTF function call, the TFTF CPU suspend function call. These changes have also been tested and verified on the STM32MP15 platform by Gabriel Fernandez from ST Microelectronics. This platform has a single cluster with 2 cores, and here's the device tree configuration that we tested the changes with. Okay, Now I'll hand it off to Maulik to talk about the testing and analysis that he did on the SC7280 platform.
Hello. Hi. Can you hear me?
Yes.
Okay. Thanks. Thanks, Wing. Hi, everyone. My name is Maulik. I work to validate OS initiated patches on SC7280 platform. So this platform is already available in upstream kernel as well as TFA. It currently uses PSCI's platform coordinated scheme, and I have I have posted already the patches to convert or use the OS initiated scheme on this platform in both Linux kernel as well as TFA. So links for both of them are mentioned here. Can you please move to next one? Yeah, so coming to SC7280 platform, it is having 8 CPUs and 1 L3 cache, and its CPU idle states are defined as state 0 to 3, where 0 is WFI. State 1 is for a core collapse, state 2 is a real level collapse, and state 3 is an L3 off. Plus, additionally, we are doing last man activity called a system resource to be voted off in the state 3. So when it comes to platform coordinated scheme, all of these are in a flattened model, in the sense state 0 to 3 are at all at CPU level and CPU governor have to select them. Whereas in OS initiated scheme, state 0 to 2 are at the CPU level, in the sense CPU idle governor have to select them, but for state 3 there is a domain idle governor to select them. Yes, thanks. So yeah, this is another view of flattened and hierarchical idle states. So you can see in the platform coordinated scheme, CPU 0 to 7, all of them have state 0 to 3 to select, and the cluster state 3 decision is taken in firmware in case all of the CPUs are okay with the state 3. So in this scheme, last CPU activity is a little difficult to achieve, and we have custom driver logic today implemented in upstream kernel to do that. In case of OS initiated scheme, the CPU idle governor have responsibility to select only amongst 0 to 2 states, and state 3 is then selected by a cluster or domain idle governor. And the last CPU activity here is a bit easy to achieve, and there is not or much role played in the firmware to make a decision of state 3. Yeah, yeah. So for comparison of both of these schemes, we have taken a use case of a 10 seconds device idle with its display on and Wi-Fi and modem turned off. So the numbers are captured in terms of two residency, and that is the time in seconds the CPU or cluster stays in a power collapse state, and the count is number of times it is entered in those states. These all taken as an average of 3 iterations for actual count and residency. Note that this is also captured with fixed CPU frequencies to avoid deviations, and this is also captured for two cases. One is with only single CPU online, and one is keeping all its CPUs online. Yeah, so when we compare the states for a single CPU, so the blue color is for platform clock coordinated mode and the black one is for OS initiated. So we do see that in OS initiated scheme or a platform coordinated scheme, because it's only a single CPU, both are almost behaving on par in terms of residency. So we see that state 3 residency is close to 6 seconds in both of these use cases, whereas state 2 is around 2 seconds or less than 2 seconds in both of them. And state 1 is very less, like less than 0.5 seconds in both of these cases. Yeah, so coming to multiple CPUs use case, so here we keep 8 CPUs online. So for simplicity, this data is clubbed for all 8 CPUs in the sense for a device idle use case of 10 seconds, all 8 CPUs are going to get 10 seconds of idle time. So the sum is or for 80 seconds time. So out of this 80 seconds, we see that in platform coordinated scheme, it is able to achieve state to residency of around 60 seconds amongst all 8 CPUs. Whereas in OS initiated mode, it is able to achieve close to 70 seconds idle time in the state 2. Whereas in state 3, that is a cluster level state, in OS initiated scheme, it is able to almost match the single CPU use case, that is around 6 seconds it is able to achieve. Whereas in platform coordinated, it is achieving around 1.5 to 1.7 seconds only in the idle state. So in conclusion, we see that when we use OS initiated scheme, it scales well with multiple CPUs in the sense it is able to achieve similar results as in what we have seen for single CPU even with multiple CPUs, whereas in platform coordinated, the deeper states residency is being reduced with platform coordinated scheme.
So question here. Uh, when you measure
Yes,
these numbers of count and residency, are they measured from the hardware or from Linux kernel stats?
they
Are-
are measured from hardware.
Okay.
Okay, any other question?
I'll have a question, I guess, at the end of the presentation.
Sorry, could you
Uh,
please
sh-
explain what does residency mean?
So residency is a time in which this particular state CPU or a cluster is staying. This is in seconds.
You mean in idle state?
Right, in idle state.
Okay, so that means there is no workload, but does it have to anything to do with which power mode it is currently in? Is whether it's in retention, suspend, or WFI?
Yeah, it is in power of state, not in WFI. So state 0 we are not capturing. We are capturing from state 1, 2, 3. That
Okay,
is a deeper mode which involves PSCI invocation as well. Yeah, so these are the states. State 1 is a core level collapse. State 2 is a rail level. And state 3 is a really a cluster state, L3 off.
okay, thank you.
I guess what would be useful is this data is good to view it from a system level because obviously Linux has to do a bit more work to coordinate the state and enter the low power down. So perhaps it's spending more cycles computing the coordinated state, although the time spent in retention or the time in residency is higher. It would be good to see, but I think these results are quite good as they are. Yeah.
So one more question over here, right? That leads me from what Sobi was saying. The domain governor in OSI mode, does that have the same latency numbers to enter into an L3 plus shared system collapse?
R- Right, right. So whatever today it is using in upstream kernel, right, in platform coordinated scheme, all these 3 parameter entry time, exit time, and mean residency for an idle state that is kept same when using OSI mode, OS initiated mode.
Okay. Which sort of means that there is an overhead somewhere in the form in TFA firmware which leads to a lower number of entries, right? I mean, Otherwise, from a hardware perspective, it's
I won't think that way. The one of the observation in the multiple CPU case is that basically a CPU idle governor is overloaded or overburdened here to select a state 3 as well. In the sense that you, if I take a simple example of state 3, for example, residency, minimum residency for state 3 is defined as a 10 millisecond and state 2 is a 5 millisecond. Now, if a CPU waking up, it sees that its minimum residency is only 7 millisecond, which is good enough for a CPU level. But the CPU idle governor could think that I have failed to enter into state 3, even though state 3 is not really achieved by keeping other CPUs online. It may still prevent this CPU next time to enter into state 3 by its own prediction or other means, so that it eliminates the chances to have a cluster level state.
yeah, that's a sensible point. Yeah, I think the prediction logic inside the CPU idle governor would then cause problems here.
Right. So ideally, I mean, we at least we think that the CPU idle governor should not invoke, a cluster decision, right? So that is left to cluster or domain idle governor now.
Okay.
Also, as the number of states in the cluster level increases, so for example, today we have only one cluster states in this SC7280, but certain targets could have multiple cluster states, right? So in the flattened mode, it would, burden, like if you have a 3 more cluster states, it will be little complex to select in the CPU idle governor itself all of these states. And that too, if in the Linux, if someone, some other driver is taking a PMQoS or some dev PMQoS on only one CPU, right? So that it is not able to enter, but all other CPUs that is, selecting a mode, it would have to select, it would be still selecting a cluster level mode, thinking that firmware will aggregate it. But that is not going to happen because you have disabled or kind of taken a QoS on one of the CPU.
Yeah.
So a question from a security standpoint, right? So in platform coordinated mode, some of the stuff is done by EL3 or so some other more secure entity, right? Now we've taken these state 3 and last CPU activity and moved it to a non-secure world. Is it possible that that affects secure world security in some way? So for example, cluster share caches and stuff, right? So can you like
No, so yeah, we have not moved any last CPU activity from trusted firmware to Linux. Only thing is certain driver would have a custom logic to do a last CPU activity. For example, when the OS knows that it is for sure going into L3 level off, it might need to do a certain global resource off. For example, it might turn off or remove its boot for a DDR, right? So we do have upstream driver in apps Linux kernel that turns off or lowers the certain global resource requirement only when your last CPU is going and you know that it is going to happen or turn off L3 cache so that no other CPU is going to require it. So this
all right,
kind of yeah.
but
Sorry, go ahead.
if that code is rogue, can it affect security of things running in secure world? I guess it's not clear to me what the security impact would be of OS initiated mode, and maybe there's nothing, but how do we know that there is nothing, no impact?
It's going to depend on which resources you're managing, right? Because if, for example, you're switching off DRAM, if secure world isn't using the DRAM block that is controlled by that, there's no security risk. If it is, then there is a security risk, and non-secure world should not have the ability to poke that at all, regardless of whether it's OS initiated or platform coordinated mode. But I agree that there is a concern there, but it's a concern that exists regardless. Because the fundamental problem is that non-secure world can adversely affect the secure world, regardless of whether it's poking, turning CPUs on or off, right?
Yeah, and that's a system design problem in your SOC itself at that point. This is not to do with PSCI anymore.
That said,
Okay, I see.
That said, I do think there is a related thing here. What is this last man activity that's going on? Because the big reason we originally didn't like that in Linux is that there are many things that obviously doesn't make sense for Linux to be poking. For example, like we just said, like RAMs, shared caches, and that sort of thing. And for other things, we don't generally expect non-PE resources to be in the same power domain. So like actually turning them off is just odd at best. And it's something we could do even if we were using platform coordinated mode, because we could do it optimistically. So I think the Linux side, our big concern was more, we don't have any numbers that show that all of the additional effort you put in here is worth the pain of fighting with that additional work, right? I think the numbers earlier today show, yeah, you can get some better residency, but they haven't entirely shown that end-to-end story.
Yeah, just to add to that, like, do we have numbers with more than one state in the cluster level? Because that means the domain governor, as you put, needs to do more work, and that might conflict with what CPU governor. So how does it take the decision? Today, the upstream, it just enters the only state in that the power domain, the cluster power domain with the upstream implementation. So it doesn't have this retention in the middle, so that like if you introduce CPU retention and cluster retention, or like the upstream doesn't support or can handle those, how well that works in terms of overall optimization. You are saying that we don't have numbers, or do you have?
We don't have numbers, but we do have targets in upstream. Some of these targets which have more than one cluster domain idle states.
Yes, but I think the way it works today is it always expects the CPU to be in the last state to enter any domain states. Doesn't like I can't have cluster retention and CPU retention. CPU retention with
Right. It
upstream
today have a
support.
limitation. Right. Today
Yeah.
Linux kernel have that limitation of a CPU has to be in deepest idle states. That is, in this case, it is second number two, state 2, to achieve any of the cluster state.
Yeah, the point was like once we get that into the mix and compare the results, how much gain do we get and how much work the PD governor has to do to take the right decision and enter the correct states, and how does this impact the overall performance? Because today that is missing, and in the comparison, it's missing from both the sides. But in platform coordination, that is possible. You can achieve that state retention at both levels. And it's like, it should come free because you're not saving anything. So how much missing that state in the GenPD, the cluster OSI mode makes is what I'm missing in the overall picture. Because in the set of state, you don't have that, but it is possible if you want to achieve that state.
Right. Yeah, please go ahead.
Oh, I just want to add, I guess the other consideration though, aside from the time spent in, the GenPD governor selecting that state, is also the power savings that the SOC gets by being in that deeper state for longer. Like I think for here, if I'm understanding the diagrams correctly, like in platform coordinated, the state 2 actually gets chosen more times, but the total overall residency is less. And so I'm inferring that, the cores, the CPUs are spending more time coming in and out of like power on and off, versus even though in OS initiated, it gets selected less times, we actually spend more time in those states. And therefore we actually, from, like the SoC, like a mobile SoC's perspective, we get more power savings.
That was precisely the point that I was trying to get at as well. I don't know whether Sudeep and Mark, you agree whether this really falls within the remit, but it seems that there is something going on with the Linux governor today that is being bypassed by using OSI mode in some way. I mean, there is either a prediction logic that's going wrong, or you are entering shallower states a larger number of time, which is being bypassed because you're selecting a lower number of states using OSI mode. Now, is that something that means it's a justification for OSI mode or not, is something we need to decide.
So I agree. There's a weirdness that we should try and investigate. I'm not sure it actually tells us either way. I'm not trying, and just to be clear, I'm not trying to block OS initiated mode here. I'm just trying to raise that there are larger trade-offs.
Yeah, and also the point you made about the latency, we need to look at how exactly the calculations are affecting both. Are they identical, or is there a chance that like one becomes a subset in the other, and the overall calculation differs in both?
No, I think domain governor uses its own latency, which is we have kept same as state 3 minimum residency and entry exit times.
Yeah, like it's the way we present to the flattened list of state. Is it like includes both CPU and cluster level, or one becomes like kind of subset and we can ignore it? So that's the point I was trying to bring up. And if the cluster residency is the latency, and especially the entry latency is apart, probably one can shadow the other, like the cluster entry latency might shadow the whole CPU, whether that's taken care properly in both modes when these numbers were taken, or they're like one gets added to the other, and we are just increasing the entry latency in one case compared to the other.
Yeah, I think so. There's something going on funny in platform coordinated mode initial code, really. I mean, because on the hardware side, nothing's changed. So the only thing that's changed is the prediction logic in this case. I don't know if Wolf is there and he would like to comment on this.
Definitely, there will be a selection differences because the GenPD governor, when it is selecting the cluster state, it has the knowledge of 8 CPUs versus when the CPU governor is selecting for the platform coordinated state, it only sees from its core point of view, right? Whatever core states from 1 to 3. Whereas in case of GenPD governor, it has a knowledge of all 8 CPUs. That's where I understand this better selection is happening.
Okay, any other questions? Ulf is on holiday this week, and he probably can't join today, so.
Yeah, I do have a general question. So this is for non-ACPI system, right? Yes, the name of OS coordinate is very confusing. In all the server power management ACPI system, our OS initiate, right? It's very popular. We have been using it for years, even on notebook.
It's, I guess the naming is the perspective of whether the platform or the OS is doing the power state coordination.
So the naming here is what the PSCI spec calls this. I think what you might be thinking of, if you're thinking of like Qualcomm SoC laptop stuff, that is entirely bypassing this from my understanding.
Yeah, so yeah, I will see if you have say an ARM-based notebook, and the ACPI describe all the hardware configuration, and then the OS is operating directly.
Sure, but in that mode, if you're using ACPI standards that describe the presence of PSCI, that it's using the platform coordinated mode. The coordinated versus initiated thing here is just about who chooses like to actually enter that last idle state.
Yeah, so do you think the like a typical notebook running Windows are OS initiated or platform coordinated?
If it's using PSCI and it's running Linux, it is using platform coordinated mode.
Then how will you know to turn off the power? Because all the power panel must be hardware dependent, right? Platform dependent.
So this comes back to the earlier point of what is the last man standing work, right? Because if your CPU power domains are separate from any other resources, then all that needs to happen is when you put a CPU in, when the CPU calls up into firmware to enter an idle state, it just says the deepest idle state I can support is being turned off. And as long as all of them do that, the firmware can just turn it off and it doesn't affect anything else in the system. There is no last man standing work necessary, right? So the big thing, sorry, go on.
But I was just going to add on top of what you said, Mark. Please continue. I mean,
sorry. Yeah, I think the key difference with OS initiated mode versus platform coordinated mode is it allows the operating system to make the choice later than it can with platform coordinated mode. However, consequently, that means that that there is a bit of additional work that every CPU must do to enter an idle state, even ignoring the GenPD governance stuff, because there may be additional state that we just have to say, assuming that it's a context, we might be placed into a context destructive idle state. For example, like saving the PMU state. And I think generally when PSCI was envisioned originally, we weren't expecting there to be shared resources that required last man standing work. So I think the last man standing work you actually have to do is the critical, important thing to characterize.
Yeah, and if you look at the ACPI spec then if you look at the LPI, then on ARM systems, when you use LPI, you by default use the platform coordinated mode and PSCI. The coordination just means which is the entity which is selecting the last core to go down, and the entity that's closest to the hardware should do the selection, and that's platform or OS is the discussion that we're trying to have here.
Okay, yeah, okay, yeah, that makes a little bit of sense. But my understanding is once the OS has all the information from ACPI, they are able to do everything, right? They don't need to depend. The firmware is already off. There is no firmware.
That's not true. Sorry, there is secure firmware. There's EL3 firmware. That's trusted firmware running in BL3, I would believe it would be. There may be stuff on the secure side that's running, but on the non-secure side, you're right. When you're in the kernel, there's no like ACPI firmware that's concurrently running unless the operating system chooses to invoke something there. But there is firmware which is resident in memory at EL3, and that's where the PSCI implementation lives, and that's what we're calling up to when we enter an idle state.
And just to be clear, so none of the correctness checks have really moved out, right? All of that still exists in EL3 as is. It's just, yeah, like you said, I think last man standing stuff is moved out of EL3, right? Which is why there's really no security potential security issue here.
So I don't even think it's last man standing stuff that's moved out. The thing that's moved out is the choice of what deepest state to enter. It's just moved to the last man standing. All of the work you have to do for last man standing hasn't really changed as such.
Yeah.
Because if you could enter that deep idle state on platform coordinated mode, you still have to save that somewhere. If it's actually functionally necessary, someone has to do it.
Yeah, okay,
Yeah,
makes sense.
and
Yeah.
that's why moving the decision really means at this point in time that we are looking at some inconsistency somewhere in the CPU idle governor, because nothing else has changed.
Yeah, and also the platform still have to take care of the race, and it will have to do like what OS thought as last man could, like by the time the platform executes, it could have changed. There would be another CPU woken up by then. So all the checks, the platform has to still take care. So that's the reason why we are thinking like how these numbers. So it's like those races has to be dealt in the ones that races close to the hardware must be dealt with in the platform if OS couldn't consider that. Irrespective of whichever mode.
Yeah, that I want to add, yeah, that problem would exist in both platform coordinated and OS initiated, in that when the OS wants to do the, I guess OS or another entity wants to do last man activity, it still have to check that we are still good to actually
Just
turn
a
off.
follow-up question, like in these cases, like the EL3 PSCI implementation bypassed the check, or they still had those checks in the firmware to handle.
From my brief look at the patches, the checks are there, it seems. Yeah, the checks are being done.
Yeah, so there's two this is kind of implementation details which we can go over the rest of the slides, but to answer your question, we are also updating the power suspend handler, power domain suspend handler, to actually return an int for like an error code, whether or not it was actually able to enter essentially do final validations based on hardware states. At least in like ARM, PPU implementations, we could have the PPUs, we could essentially put the PPUs in lock mode so that once it actually enters the power down, that it won't come out from an interrupt unless a separate entity like an SDP unlocks the PPU. And so we won't consider suspend for a cluster state to be successful unless like the firmware, like the platform power domain suspend handler, can lock the PPUs.
So are you locking the PPU from your power domain suspend handler, from your power domain governor here in this implementation?
So in our Google platform implementation, we are doing that in the platform power domain suspend handler. And so, but then with the platform coordinated, we would have to actually do that like in the OS, well, not OS, but like OS has to notify a separate entity to do so. But then at that point, that might fail because the PPUs might not be lockable at that point.
Okay. And
As
there's
in
any
there-
particular reason why you're using that? Is there a PPU autonomous mode on your platforms as well that you could use, or is it a PPU that has to be locked and you do not support autonomous mode on your platforms?
So we are using dynamic mode, but say if we want to turn off like a shared rail, when say the last core in that, so the last core in that cluster would lock itself, but then it would also have to lock its siblings. And so it has to successfully lock its siblings before we consider we're able to like suspend, because if it can't lock its siblings, then we can't enter that cluster idle state, because we can't turn off the shared rail.
Okay, so you're physically turning off a shared PMIC rail, not a
Yes.
power domain. Okay, fair. I understand that then. And that's dependent upon, and you've got a dependency on the PPU sequencing on that.
Yes.
Okay.
Hi, Varun here. So one question, during your analysis, did you find or did you get a chance to benchmark the governor where the OS mispredicted the state entry? And because looks like, I mean, in the initial slides, you said that we have a side channel and that was the reason we looked at it. But I think there were some comments that the governor might be mispredicting. So just want to check if you went down that path and figured out that the OS has been mispredicting the state entry, and that is maybe that is also maybe causing the higher numbers. I hope I was audible.
Yes, you were. Well, Maulik, do you want to take that question or?
Sorry, can you please repeat what is the?
Yeah, just wanted to check if you have any numbers where the OS mispredicted the state entry itself, and maybe because I mean, looks like that might also be one of the reasons for the higher numbers that you were seeing earlier.
No, we don't have, but yeah, this is all for the actual entry. So
okay,
this is all for hardware calculated entries and counts, right? So
yeah, I mean, if we are looking at the governor having these kind of issues, then we are looking at a bigger problem. So, and yeah, for this, maybe it will affect more platforms. So I think that's a bigger issue that needs to be checked.
Well, Ulf is not here, but I think like the whole rationale for the Linux kernel to add the essentially the CPU power domains to the GenPD is to represent like an SOC or like a more complex SOC, like higher power domain hierarchy better, and to be able to have the GenPD cluster governor make these decisions as opposed to the CPU idle governor independently for each core making their own decisions. So I think I guess what I'm saying is most SOCs with more complex power domain hierarchies would prefer to be using the GenPD domain as opposed to just the flattened CPU idle state domains.
Sure, I think it also depends on what the platform power management policy looks like. I mean, if there is just a plain PPU that's handling and there's no other power management controller in the system that understands the topology and is not playing any part, then yeah, sure. But if there is also another PMIC or a power management controller at the lower level and it understands this, then I think it is better suited to make these decisions. And then for those platforms, it makes sense to push it down into the firmware.
Right. I agree with that. Okay, so we have 8 minutes remaining. We do have some additional slides to go over, but I think I'll just skip to. So mainly it's just kind of like requirements and how to handle certain, race conditions. So I'll just quickly highlight that, race conditions can happen because the OS can make a request and it, conflicts with the implementation's view because the implementation might see, a core powering up in a domain that the OS might want to put in cluster state. And so the main thing that we have to do in terms of validation in the PSCI implementation is that one, it has to, well, the OS one has to specify the deepest core that it sees the calling core as the last man. And then two, the PSCI implementation has to make sure that the calling core is really the last core to go idle, so that it can actually validate that the request is valid. I was going to go over examples of the race conditions, but it's actually in the spec, so maybe we will skip that unless we really want to go over it. Maybe we'll go over the second one, second example. So in this example, initially core 0 is in power down. So this is the same topology as the one we saw earlier, where we're essentially looking at cluster 0, core 0, and core 1. So initially, core 0 is in power down and core 1 is running. And core 1 wants to go idle. The OS requests for core 1 to power down and cluster 0 to go to retention. But at this point, core 0 receives an interrupt. It wakes up and moves into the OS to start processing interrupts. And then when it's done, it goes back up to idle. The OS requests for core 0 to power down and for cluster 0 to stay running. So at this point, the the platform, like the PSCI implementation, hasn't actually processed either request yet. And core 0's request overtakes core 1's request. And then it puts core 0 to power down and cluster 0 stays running. So the problem here is, even though the OS made a request for the cluster to run, the implementation doesn't know that this is actually like a cluster state request, and to reject core 0's request because it doesn't know that that information. And so when core 1's request gets observed, the implementation puts core 1 to power down and cluster 0 to retention. So what should have happened is that both cores, when they're making their idle request, should have identified themselves as the last core in cluster 0. And this way, when the implementation sees core 0's request, even though core 0 overtook core 1's request, the implementation rejects it because core 1's still running and it involves it's a cluster state. And same thing for core 1's request, where core 0 is still running, and so it rejects it. And at this point, the OS can reevaluate the idle state on both cores. And then this is the current implementation of platform coordinated mode. The one thing I want to highlight here in the interest of time is that there is a function called PSCI do state coordination, where the platform, the power state coordination that we've been talking about happens, and it updates this state info object with the coordinated target power state for each level. Okay, so the proposed changes, we have 3 minutes. So the main thing is we are adding a Boolean build option so that each platform can, decide whether or not they want to enable OSI mode. And yeah, the changes will not be compiled into build if this option is not enabled. And then I will skip these. So for CPU suspend, the main thing that we're doing is adding a new function called PSCI validate validate state coordination. And it will check that the requested power state, the requested power states are consistent with the system state, and that the calling core is really the last core running at the requested level. This is different from the PSCI do state coordination, since we're only modify this global data structure that keeps track of all the requested states called PSCI requested local power states. only if the request is valid. Otherwise, we won't modify that. And then also we're not modifying the state info argument since it contains the actual request from the OS. And then the last thing is that, yeah, we'll call either PSCI do state coordination or validate, or PSCI validate state coordination depending on the suspend mode. And then the last point here was kind of one of the questions earlier that we'll update the return type for the power domains suspend handler to actually be able to return an int so that we can know whether or not the suspend was successful from, like, you know, based on like whatever the hardware states are, so that the platform itself can do some final validations. And that's it. Any other questions?
So on the last slide, will the power domain suspend also return an int if we are using the platform, if you're not using the OSI mode?
No, so if you're not using OSI mode, it's still going to be void. It's
Okay.
will be guard. The function definition will be guarded by the that build option here.
Okay.
So for platforms that don't want to use OSI mode, it will work exactly the same, and all the extra code will not even be compiled into their build.
Right, and I guess the validate, the new handler that was added in the PSCI code, so that would be the point where you lock the other cores, so that any core does not wake up past that point. I mean, that's.
Yes, that's kind of, at least for, sorry. But yes, that is at least in our implementation, that's how we're implementing it, is that is kind of our point of no return, is that when we are able to lock the sibling PPUs, we can perform those last man activity and consider it suspend to have been successfully entered.
And did you have to make any changes on the Linux kernel side, or you just use the kernel as is, but make the changes on TFA and then get this to work?
Yeah, we're able to use the Linux kernel as is with just the device tree, using that hierarchical domain structure to take advantage of GenPD.
Okay, thanks.
Just out of curiosity, how were you doing this before OSI mode, the locking?
So we are having essentially the OS. So there's like the side channel that we're using is the like inform registers, where the OS writes to the inform register to you know, indicate its intent to like go into, you know, like a cluster state. And then when the core goes into idle, there's another SCP that actually does, you know, gets the PPU interrupt and then attempts the locking after reading the inform register written by the OS.
Okay, thanks.
So we're more or less at time. What I suggest is if there's any more discussion on the, you know, the concepts of the modes and things like that, that we take that to the mailing list. The patches are available for people to review, and further discussions can be had there. I will make available the recording and the slides when they're made available to me to put on the TFA Tech Forum page. If after the any mailing list discussion we decide we need another live meeting to discuss, we could happy to schedule another one of those. From my point of view, it's good to see test here as well as the implementation. That was quite important for sort of submitting to the project, so that's good. But the patches themselves for TFA tests and the implementation here can be reviewed and comments made. Yes, thank you for your time. Is there any last comments you want to make?
No, thank you, everyone. It was a very good discussion.
Okay, well, we take the discussion on to other means in patch reviews and the mailing lists. And as I said, I'll reschedule another meeting if everyone decides that a live meeting would be beneficial. Thank you, everyone.
Thank you.
Thanks, everyone.
Thank you.
Bye.
Bye.